Now, it is my great pleasure to introduce our first keynote speaker, Dr. Marwan Nadar. Dr. Nadar is a globally recognized expert in long-span bridge engineering, seismic resilience, and structural innovation. As a Senior Vice President and Technical Director at TY Lin International in San Francisco, he has played a pivotal role in the design and advancement of some of the world's most iconic bridges, including the San Francisco-Oakland Bay Bridge self-anchored suspension span. His work integrates cutting-edge engineering and practical solutions to enhance seismic performance, sustainability, and structural efficiency. With over 3 decades of experience, Dr. Nadar has led groundbreaking research in cable-supported structures, seismic retrofitted, and advanced material applications. His contributions have not only shaped major infrastructure projects, but have also influenced best practice in seismic design and resilience worldwide. Today, we have the privilege of hearing from one of the leading minds in structural engineering, whose insights will undoubtedly inspire new ideas and discussions. Please join me in welcoming Dr. Marwan Nadar.
Well, good morning. It's my pleasure to be here and share with you some of the lessons I've learned throughout the years and working in the industry. When I started first my career, I actually came in as a young graduate civil engineer to UC Berkeley, and all I wanted to do was get a master's and basically go on with my life. And Loma Prieta earthquake occurred, and it shaped my life. It made me understand how vulnerable we are and how Mother Nature does teach us lessons, and there's more work to do. So I decided to do my PhD just because I was very interested in doing something that could ultimately change society and people's lives in a major way. After that, I had the privilege of working a little bit at UC Berkeley, did a postdoc, but then decided that my passion is to really go out there and do work and actually work on projects. So I joined TY Lin and never looked back. It's been a great ride, and I've had the privilege of making with industry leaders throughout. Today, what I want to do is share with you some of the ideas that we've had. A lot of them are basically coming from Park and Pauli, coming from Priestley, coming from Sibley, coming from UC Berkeley. All of it is ultimately culminating in us doing that. I think we do know what we need to do as seismic engineers, as bridge engineers, as building engineers. The issue is what Mayor Brown just told us, is to actually design something that is sensible and design something that's robust, that is redundant, because guess what? The earthquake will not be what we put in our computers. It's going to be different. And we sometimes, design it to be exactly responding to the exact demands, as if you have gravity load, and you know what that is, but the earthquake is different. The frequencies are different, the liquefactions are different, and therefore you have all sorts of variables, and therefore the structure is subject to different types of loading. So with that, I'll start. Hopefully this moves. Yeah, there it is. So owners today are always looking to link up either old structures, replacing them, rehabilitating them, and replacing them therefore, or looking for new links around the world. And by doing so, they're investing billions and billions of dollars. And in doing so, the first question is they want to protect their assets. It's very simple. The codes say one thing, but they look at these big project costs that they have, and they ask, what can I do to make sure that my asset is protected? And most of these projects tend to have large mega bridges in them, long span bridges in them. So what we are doing is looking at how we can make sure that the performance of these structures is protected and the asset is protected when we are designing and putting the project criteria or the master design criteria for these projects. So the first thing related to this particular conference is obviously the seismic hazards and the ground motions. And any big structure, you're not just dealing with seismic. You all know that, right? We saw what happened with the Key Bridge in US when a vessel hit it and collapsed it very quickly. And any one of us in this room would have probably been able to predict that. We actually look at that pier and say it's a matchstick standing in front of a big barge. There's no way that it is going to be okay. In fact, as we speak, the NTSB in the US published a report, and we have about 17 or 18 of our mega bridges, including Golden Gate Bridge, including Brooklyn Bridge, that are actually susceptible for vessel collision, and we are looking into reinforcing those and making sure they're protected for that. So vessel collision is one. The other one is wind. We all know about wind. You know, we've seen some structures collapse in the past, but again, it is one of the major elements. Tsunamis is a third one. And obviously, seismic hazard, which causes tsunamis, is the subject of this topic, and it's probably the most wild one of all of them because it's not really, a lot of probability goes into it. So the first thing you do is you try to get your hands on what is the seismic hazard. What does that mean? Obviously, we all know it. It's very well represented in a response spectrum. Where is your energy in, at what frequency? It's very easy to shake a table. Are you shaking it very fast or are you shaking it slowly? Those are things that matter. And then two, what is the soil underneath that? The soil, is it sitting on rock, or is it sitting in a bowl of jello that shakes, or is it going to liquefy? Those are things that are major, major drivers. The most important piece of it all is when you're dealing with a long span structure, you could be shaking like this on one pier and like that on another pier. And that's why most of our bridges collapse. That's why what happened in Myanmar, some of those projects, when you look at them, the multiple spans, you saw some trusses fall down, the others didn't. That's because simply the displacement exceeded the bearing displacement, and it fell over. The structure would have been perfectly fine if the engineer just had a little extra, probably. Yes, it probably would have got damaged, but potentially not collapsed into the water. So what we do is we look at performance-based seismic design. What we are doing is we are looking at what is it that we want out of our structure. Are we looking for our structure to not collapse? Are we looking at our structure to save lives? Are we looking at our structure to have the ability to have emergency traffic on it? In other words, is it what we are referring to these days as lifeline structure? Is it a route that is very important, that after a major earthquake, when your fires are out, your buildings are down, and you need your emergency personnel to travel from one point to another, this is your lifeline structure. That's the structure you want it to stay there. So therefore, it has a higher standard of performance. Those are different levels of performance, and they actually drive a lot of the discussions. What's interesting, I've been in many, many conferences where people start talking about, oh, what's your maximum credible earthquake? Oh, are you designing for the maximum credible earthquake? Or what is your return period? Is it 2,500 versus 1,500? Oh my God, you're designing for 1,500, therefore your bridge is no good. It's absolute nonsense. What matters is what are you designing and how are you going about it? Are you doing pushovers after that? What happens when the loads do exceed those demands? And is the structure going to be okay? So looking at it from a macro picture about performance-based design and the levels that you're designing for is really where the rubber hits the road. So when we look at the design, the performance-based, and once we get there, now we look at what does it mean to have a capacity-based design philosophy? It's simple. We all drive our cars. We all know that we get into an accident. It's inevitable. It's what's going to happen. So what you do is you design for fenders to take most of the damage. And then you design for a seat belt, obviously, to hold the driver. You have the airbag. But bottom line, you're planning for this to happen and making sure that the car system at the end of it is not going to basically break apart at the axis itself. You're trying to have a sequential way of damaging things. And in earthquake engineering, if you actually work with a capacity-based design method, you have these weak links, you might call them, fuses, like the fuse box in your house, when electric jolt comes in and it burns up rather than having you to replace your refrigerator. Those elements become the key components of you being able to design. It could be plastic hinge design that you have. But most importantly, you have to ask yourself, what if things do change? What does that mean? And more important after that is, if they do form a hinge, can you repair it? Can you inspect it? Can you look for what happens next so that you are in a position where you can have the performance-based design that you're looking for? So in seismic engineering, That's the capacity design. The second is really to use our technology today to actually be able to capture the demands. Now we've established the seismic hazard, we've designed our capacity design philosophy. How do we go about establishing the actual demands? And that's not a straightforward process. However, I think a lot of us in this room would say we know how to do this. Problem is, it's too dangerous of a tool in the hands of young kids that run these analyses, and guess what? They look damn impressive. And when you have them, you will believe them, and therefore you'll design for them. But the key is to actually always go back to the basics. The structures are rather simple. You don't want to overcomplicate it, and when you think about it, you can probably, within a month or two, figure out what the demands are. So as I always say it, you can go and run the analysis all you want. What matters to me at the end of it is you can show me your force diagram and the force flow, and convince me that you've got the right displacements. And we look back at the response spectra, we can draw the displacement spectra and find out what the maximum displacement is so that your structure is designed for that maximum displacement. I don't know, I don't care if your time history says you're gonna be displacing about half a meter. What matters to me, if your displacement spectra at that period you have says you're gonna reach 0.75, you'd better design for 0.75. It's very simple. Your ground motion content, the time history, happens to be such that it's seeded, that it doesn't have that, it's not doing its job to make that displacement be at 0.75. Two, you are going, all the ground motion is pumped from the ground up. So if you think about it, getting that piece of the equation is very important. So the soil structure interaction is a fun, nice, sexy word. And back in the day when I started my career, structural engineering like myself would never touch it. We would give it to the geotechs to deal with it as if it's their job, and then our job is to take those ground motions at the foundation level, at the pile foundation level or the pile cap, and pump that into the structure. But what you see in this image here is you see the whole piling system, and you see the old PY and TZ springs, and you see the nonlinear behavior of those elements. And that allows you to not only do what get the actual ground motions that's seeded from the ground rock crop into the actual, but do the depth varying motions and the multiple support excitation that I talked about when one pier is shaken that way and the other one is shaken that way. You do that, you get a lot better sense of that complex nature of how the structure is going to perform during an earthquake. So I am going to walk you through two projects that are dear to my heart. One of them was something that I started in the early 2000 and opened to traffic in 2013. I'll tell you, I have another story at the bar if you want as to why it took that long, but it's not by engineering, I can tell you that. A lot of politics involved. But the key is that it started in 2000, and at that time, the whole concept of what I just talked to you about was just coming into the actual practice world that we had. There was a lot of research being done at UC Berkeley, a lot of research done at UC San Diego, in New Zealand here, across the world, learning from lessons as well, but it wasn't really taking into the actual application of building and designing bridges. The concept of putting a damper on a bridge, or a viscous damper, or an isolation piece, base isolation, or putting a fuse was something that owners didn't want to deal with. So there was a lot of brain power that got involved in this. If I start the list of telling you the people that were involved, I wouldn't finish today. There was about 30 scholars that were all involved in performance of this bridge that you see there. It's a major one because in 1989, that existing bridge, the east spans of the San Francisco-Oakland Bay Bridge, collapsed, closed for 1 month. But at that time, that 1 month was estimated to cost the San Francisco-Oakland Bay Area about $200 billion in cost revenue. So what happened, the governor at that time decided this is not good for Route 80 because Oakland, San Francisco is connected. They wanted to make sure it's a lifeline structure. Bay Area at that time was going through the whole dot-com boom. They wanted something sexy. They wanted something unique, something that looks special, and you can only find it in the Bay Area. So there was basically two driving factors. You've got the governor wanting to have something safety for the public, and the other wanting something iconic. So that's a challenge we love. And on top of it, it sits in a bowl of Jell-O. So basically, you had three competing pieces coming in to that. So we had a design competition, looked at cable stay bridges, looked at self-anchored suspension bridges, looked at arches. Ultimately, the self-anchored nature of this unique structure with the 3 dimensions one. I can give you a whole documentary about the aesthetics values of it and the debates that went through it. But bottom line, what was number one rule is that no matter what you design, it has to be safe and it has to meet the performance-based criteria that I just talked about. So the bridge itself is about 3 kilometers long, has a signature span, which is the self-anchored suspension bridge, and has a viaduct for the other 2 kilometers with it. It sits right between the Hayward Fault and the San Andreas Fault. San Andreas Fault, for those of us who like history of earthquakes, 1906 earthquakes in San Francisco destroyed the city practically. It was about an 8.1 magnitude earthquake, but if you look how close it is to the city, it runs across the Pacific north-south, it is just dangerously so close to the near-fault effects. And again, I'm not going to do this with this table here in front of me, but I still remember as a student when Professor Bertero grabbed the table in the room and he said, you know what an earthquake near the fault does versus not? He said, if it's far away, it shakes the table back and forth like that. But if it's next to you, it takes that table and he barged it. He said, that's what a near fault earthquake does. That's exactly what it does. It actually shoves you to the left or to the right. And that's what collapses bridges. Those kind of earthquakes are going to occur in that Bay Area. And that's a metropolis. And to make it worse, Hayward is right next to it in the hills over there. So we're sandwiched between 2 active faults that definitely talk about hazard and seismic hazard. It is there. The soil profile is terrible over there. 100 meters deep bowl of jello. Bay mud, it has a name for it. And it actually, I can tell you, when we were driving these piles, large diameter piles, into the soil, to reach the rock or to reach 100 meters deep, because that's what we needed to do. The piles for the first 30 meters sunk by themselves. You did not really need to drive them down. So the first 30 meters is just, passive and doing nothing for you on these soils. At that time, we worked with Fugro, who was the leading edge in marine geotechnical investigations, did a 3-dimensional survey of the whole bridge, geophysical, with boreholes. We understood the whole soil profile underneath it. In fact, the alignment of the bridge itself was chosen so that it is not as north as it should be, because they wanted sweeping views of San Francisco as you're driving towards it, because we were afraid we're going to reach an area where there is actual soil instability. The spectra that you see there is very interesting. You can see a big bump in one of the longer periods, very unusual for a spectra, and that's probably part of the reason why in 1989 the actual existing bridge collapsed, because the bridge was kind of long period, and for it to fail for a magnitude 6.9 earthquake, which is about 30 kilometers away, was kind of odd. But it did happen because one of the soil structure interaction interacted that way. Now, the seismic performance criteria, one of the things that happened, which was very interesting, and again, I'll say it now, because back then, most design codes, AASHTO, any code you design for, the design life of a structure is 75 years. Now, that sounds odd, right? I mean, you put something out, you tell the owner that, hey, in 75 years, you probably have to replace the bridge or, do something about it. What are you talking about? 75 years? No. My bridge or my build, it's going to last a lot longer. This is nonsense for you. So there's 2 terms now. There's a design life and a service life. And the idea with the service life is what you do is you keep servicing it, it lasts longer. Perfect example, Golden Gate Bridge, right? Built in 1930s. I think for those who watch Star Trek will agree that when the spaceship Enterprise came into San Francisco in year 3000, the whole cityscape was different, except the Golden Gate was still there. So that kind of gives you a perspective of how much people like their bridges. But at the same time, what does 150 year mean? Is it better than 125? What does it really mean? And it basically, forget the service life for a second, the design life. What it means is simple. You design for 10% probability of exceedance versus the design life. So everything is changing when it comes to maximum earthquakes, maximum wind loads. All of these pieces, vessel collision, because all of these are probability based, and therefore your maximum loads are increasing. That's primarily what it's doing. Now with durability, you're working towards a program that gives you also the 150 years. And what that means, is the onset of corrosion cannot start before 150 years. Now, if obviously we all know you have a car, you paint it quite a bit, then it lasts longer. So obviously maintenance and operations has a lot to do with how long your structure lasts. But the key with these 150-year design life when it comes back to earthquakes is, again, what it does for our performance-based design. And do we design for a safety evaluation earthquake at that time? That's what we talked about, or a functional evaluation earthquake. So people started talking about what does that mean? And at that point, we landed at a 450-year design life for, return period for a functional earthquake, and a 1,500 for a safety evaluation earthquake, and came up with the criteria that are associated with both of them. Now, the design philosophy was limited ductility structure, primarily because the structure was a lifeline structure. It was not going to sustain damage such that after a major event, within 24 hours, yeah, some people didn't want to say 24 hours, but I say it, within a day, you can have emergency vehicles on the bridge. That practically trumped everything else. Functional earthquake we practically designed the structure for a functional performance at the safety evaluation earthquake. However, we did not want to design for the very large event. So what we started thinking, scratching our heads, what do we do to design the bridge for an earthquake so that we can use some of that seismic ductility, we can use some of that seismic performance fuses that we had. So I was lucky enough, when I was doing my research at UC Berkeley, Igor Popov was doing the testing of the shear links at that time. And those were for building eccentric braced frames. And I remember seeing how much they behave. So I called up Popov and I said, this is what we have. I'm thinking of putting shear links along the height of the tower. Would you think that's a great idea? Couldn't leave the TYLN offices for about 6 months. He was so happy about it. We ultimately devised a research program and tested it with Frieder Sibley and UC San Diego. But the idea is simple. You actually design a single tower that is split into 4 shafts, and you have the links along the head like a ladder. And then what you do is those elements you basically are designed so that they yield during an earthquake so that the actual shafts are not damaged at all. And the remaining of the structure is a skyway, which is a precast concrete structure. And it is designed for 6 lanes in total with a multi-use path. It has 4 frames in total, expansion joints between them. This is a cross-section of it. And the key to the performance of the skyway, as we call it, was simple. You batter the piles so that you actually do not have a lot of displacements into your pile cap. And then everything is, for all practical purposes, essentially elastic. You are taking the grunt of the earthquake. The benefit is that you just had a long period structure, and then you took it all up to the superstructure there. And then between the frames, we designed these fused beams. And these fused beams are basically designed so that in an event of overload, they are the elements that will actually yield. Now, that's key here. We are not designing the pipe beams to actually fuse during a major event like a safety evaluation earthquake. We're not. But in the event that loads are more than what we expect, this is the fuse that we are designing for. Now, back to the self-anchored suspension bridge, a very unique structure. It's the cable, instead of anchoring into the ground, it's actually anchoring into the deck itself. The cable itself is 3-dimensional. And to build the bridge, you have to build it on false work because it's not capable of carrying its load during construction. The main span is 385 meters, which makes it the longest self-anchored suspension bridge in the world. On top of it, it's not symmetric. So basically, if you do have plastic hinging in the piers or anything like that, there is a tendency for the bridge to tip to one side. And that was, from east to west, and that's not a good thing. So basically, we designed a counterweight over the west pier where it sits over rock. And the intent there is to make it basically symmetric over that single tower. The next image here shows you the cable in 3 dimensions. Most suspension bridges in the world do not have 3-dimensional cables. In fact, just building a 3-dimensional cable is a science in itself. And these 3-dimensional cables are basically taking the catenary action in both directions, vertical and transverse, and that's why you see that parabolic shape of it on both sides. This cable was designed with prefabricated wire strands, high-strength rods. The key to it is just that each one of these 5.4 millimeter zinc wires can hold practically a Toyota car, Prius. It's a very strong wire. I just wanted to give it an image because sometimes we think, okay, what's a cable really doing? It's carrying the whole bridge. And some of the dimensions or details that we have, which have very little to do with earthquakes, was a first of its kind looped cable around the west anchorage so that we can actually have the cable start in one end, go over the tower, loop around, and come back. A lot of new technology was developed for this bridge. On the other side, it anchors into the east anchorage, into the cable, and that's where the cable splays out into the east anchorage. The key is the components. I talked a little bit about potential failure of elements on the actual piers. And in this case, you see some colored elements. The blue are the shear keys, the yellow and orange, or the yellow is the bearings, and the key is to have the redundancy. The way this was designed is that the blue is carrying all the shear, which is the shear key, carries no vertical load, but at the same time, if the shear keys were ever to fail, the bearings had gaps in them, because the bearings are carrying vertical load only, had gaps in them so that they will displace about 10 millimeters, and after that they can carry the load themselves. So again, you're thinking always, what would happen if something does fail, and is it going to be okay, or does that mean that the bridge is going to get into a problem? Back to the tower. It's a steel tower, stiffened, box girders, practically, that are designed to have in themselves the ability to have basically a good plateau in compression for them to be a very compact section. And then the white elements that you see are the shear links. And the shear links had a whole science to them, but the most important element to it is that the actual webs of the shear links were designed with specifically the steel type that had a maximum limit on the ultimate strength of the steel. Why? Because we want to make sure that it is an actual fuse, not that stronger is better in this case. In fact, stronger is worse. We want to make sure that these things do not have overstrength so that they don't subject the vertical towers to more load. The tower shear link itself, you see it here. The image on the top is a rendering, and the image at the bottom is actually the tested component at UC San Diego. We also tested those at University of Nevada, Reno, and you see an animation of it on the area that are turning orange is where the yielding is. Everything else that's remaining in blue is basically elastic. The box girders are orthotropic Dex box girders, closed sections. Just because of the seismic criteria, the actual orthotropic design became very much a big anomaly, because usually you like these to be very thin-plated structures, but because we wanted, Caltrans wanted to have that extra, what if, we know that the box girders are designed to remain elastic, but what if the overload happens? Does that mean that my box girders are going to buckle? So we actually designed them to be compact, again, to take that extra strain, which is about 2 times yield, before you have real problems in these elements. So the orthotropic ribs were thicker than the typical orthotropic rib that you see on a suspension bridge. Now, I talked about the global analysis. I'm not going to go into too much detail for it, but basically what we did there is we ran it in Adena at the time. Remember, we're in 2000, 25 years ago, believe it or not. That run that I show you here would take us about 4 days before we get the results. This was how big the models are and how little our CPUs were at that time. So it was a very big investment. We run the run and we wait, and then we get it. And then the problem was we get it and so much data. Forget post-processes with standard software did not exist. So you had to go in and yourself do the post-processing. It can be overwhelming in its own self. So, but bottom line, the multi-support excitation, the depth varying motion, all the ground motions were pumped into a PYTZ springs, and from that, come back to the maximum displacements I talked about. So we did all that runs. I came back to my response spectrum, looked at my mode shapes, and found out what are the displacement, and do they make sense, and are they consistent with response spectrum analysis? Sure enough, most of the time it was. Second, we looked, where is my damage actually occurring? So we looked at that, and we found out that, yes, it is occurring in the shearlings, in the east and west spears, exactly where we want them. And what is the level of damage? And you can see the middle image. I want you to focus on the bottom middle image there, which shows the pushover of the tower. That vertical line is where the actual displacement, that 1.0 or 1.2 meters top of the tower displacement is. But look what the tower can do beyond that. The tower is not going anywhere. So that gives you a lot of comfort in knowing that the shear links are working and your vertical shafts are working and everything is going to be robust. Again, the images on the left and right, you see that the actual time history is all within the envelope of the east and west spears. Very little yielding going on as far as these elements are concerned. Now we go to something that's happening as we speak. We move all across the Pacific towards the Philippines, very close to where you are. And this is a project that we've been working on recently, the Bataan-Cavite Interlink Bridge, targeted to open to traffic in 2030. It's a major, major bridge that crosses the Manila Bay. And anybody familiar with the Manila Bay, it's on the top over there. Don't look at the lake, the body of water above it. And you can see Corregidor Island there. That's a famous World War island that was very instrumental. The bridge is going to cross the mouth of the Manila Bay, 34 kilometers in total. It has basically two major navigational channels because the port of Manila is inside. And it is going to create a completely different area for Manila to grow into, which is the Bataan side. The Bataan side is undeveloped. The Cavite side is completely developed, overcrowded. If you've been there, 3 kilometers will take you an hour to drive from one side to another. So this bridge will provide a route to an area which is undeveloped, and if it's done right, it can provide a lot of growth for that area. It's part of the Build More program, and it is very much supported by the community there, all of Philippines, and most importantly, it's funded by the Asian Development Bank. We won that project just before COVID hit. So we were all planning to move and travel and go back, and COVID hit, so we learned to work with teams, to work with the client towards developing the project and how we go about it. 2 lanes in each direction with a shoulder, but I can tell you, anybody that goes to Manila knows that this is going to be a 6-lane bridge because they drive on every single inch of pavement that you can find. So the highlights of it is that it's a 100-year design life. And you know, again, it took a lot to move them from 75 to 100. Just that simple movement of making them understand the value of it. Obviously, it impacted the vessel collision. It impacted the wind, as I mentioned, the tsunamis. You have it. You name it, they have all of that in Manila. And obviously, earthquakes are huge in that area. The bridge itself is, the majority of it is a viaduct, a marine viaduct, but again, sits in very deep water. Unlike the Bay Bridge, which sat in very shallow water for practical purposes, the deepest part was about 20 meters, 15 meters. The deepest section here is about 60 meters deep. So obviously, some of these long spans are needed for the navigational channel, but more importantly, you're driving piles in very poor soils in some conditions, but you're also having to rise up another 60 meters to get to the water level. The project is divided into 7 packages. Really, it's 6 packages. The last package is to really pave it and make sure that the whole bridge is looking consistent. The 2 packages are on either side of Corregidor Island. The crown jewel of it is the cable stay bridge, the South Channel Bridge, which is a cable stay with 900-meter main span, single tower. And you can see here the ships that go, and those are going to be huge ships. So the vessel collision is a big deal here for us. And in fact, just about when we're approving this, the FSK happened and the collapse of that, and I had to go to the secretary and show them what we're doing to kind of convince them. And all they wanted to know and hear is that if a huge, big vessel hits the tower, nothing happens. Well, something is going to happen. The bridge is not going to collapse. So we had to walk them through all of that to get convinced with it. The tower is a very tall tower at 300 plus meters, stands. To give you a perspective, if you bring the Eiffel Tower and you put it next to it, it'll stand 2/3 of the height of it. So it's a very, very tall tower designed to remain elastic. Plan and elevation of the bridge here is shown. And what you see is that the backspan has two anchor piers. One, this is basically to help with uplift on the backspans. Similarly, on the other side, the North Channel Bridge, you have a smaller version of this South Channel Bridge. It's at 400 meters in total length, but very similar in basically layout and spans. And then this shows you just a rendering of the marine viaduct. Most of the spans in the marine viaduct are 60 meters, heavy lifts, span by span. And then in some other areas, we go to 100 meters. So the seismic criteria on the bridge are nothing different than what we deal with. You look at the standard codes, you evaluate what they are, and you decide this is the design, master design criteria for it. And then after that, basically you develop the seismic hazard. But what I want to take you to is the levels of earthquake that we had. And here we had 3 different levels of earthquake that we designed for. Again, most of the time what you're doing is you're working with the local codes, international codes, and ultimately working to develop a performance criteria that applies to your bridge specifically. In this case, the one that is most interesting is the 2,500-year return period that we had, and what we do with that and what the performance of it is. In the nutshell, what I can tell you, in both of these projects, the main criteria was for us to protect the asset. This bridge here, and because that question was asked to me so many times, is the San Francisco-Oakland Bay Bridge designed to be better or safer than the Batanka VT? And the answer is they're very close to one another. The difference is that this one is not designated as a lifeline structure, but at the same time, this project here has a very important criteria in terms of limiting the amount of yielding that occurs in it. So there was not a lot of need to actually have fuses on this structure as much as just increasing the damping on the structure so that we make sure that the structure is not going to be subjected to larger loads unnecessarily. So the seismic criteria analysis requirements, again, we did a time history analysis, a pushover analysis, all the stuff that you would do. Again, it sits between 2 major faults, not too far from where the bridge is crossing. A very comprehensive geotechnical campaign was done to understand the soils and, more importantly, to develop the spectra. We had 2 different spectras along the length of the bridge because the actual rock looked very different in one area versus another. And obviously, we ran 6 ground motions that were developed for that specifically. This shows the global model of just the South Channel Bridge with the HLA elements in it. But remember, this is a 34-kilometer bridge. So we actually had a model from end to end running it. Now, get this. It's this model today, we run it. It runs in 7 hours. Gives you the power of the CPUs that we have. And it's probably, by my guess, it's about 100 times larger than the model that we ran for the San Francisco-Oakland Bay Bridge. So again, the analysis approach was very similar. We designed for multiple support excitation, We ran it with, we did the depth varying motion, accounted for liquefaction. There is a lot of liquefaction that occurs in that area. So we did all of that. And when we evaluated where we are going to have any damage on the bridge, we quickly recognized that we would like to use seismic devices to help us with the design for that. Now, one thing which is very unique here is we looked at the foundations of these big caissons under the tower. And the tower, as I said, it's a very tall tower, and we could design it into piling that goes into it. But like the Rion Bridge, and for those of you who are familiar with it in Greece, we actually contemplated of having an isolation under the big caisson. And the caisson is 100 meters in diameter. It's a big football field. This is how huge the caisson is. So we actually decided to drive inclusion piles in the actual soil to basically improve the performance of the actual soil bed and dig out the area so that we have a gravel bed above that, and then lay the caisson on it. And then after that, you would build your caisson on top of it and then build the tower on top of that. So what you're practically doing is isolating your caisson from the ground underneath it. So that's an image of it. And again, it's very important to note that the actual piles are inclusion piles that do not connect to the actual caisson above it. And therefore, it is there to improve the bearing capacity of the actual soil underneath it. It's there to not but allow the caisson to move. And obviously, in this case, the caisson is so wide, it does not uplift at all. So you basically are isolating your foundation of the pylon from that. By doing that, we actually reduced the seismic demands on the cable stay bridge by 30%. It's as simple as thinking, what can you do to actually, rather than anchoring into the ground, you're actually isolating yourself from it. This is what shows the modeling. All the PYTC springs in this case are coming from that inclusion pile analysis with the geotech in this case giving us those parameters to put them in. We had gap elements to allow for uplift if it does happen, friction elements, and we ran all sorts of envelopes. What if the friction is this low? What if the friction is that high? And then we ran different soil springs. What if the soil spring is this low versus soil spring is that high? And what happened here is, hopefully it moves. This shows you the actual caisson sliding back and forth. And what's interesting about it is that it moves about a foot or about 30 centimeters. It's a lot by any measure for a foundation to do that. But when it comes back after the earthquake and we run it back and forth, that amount comes down to about 5 to 10 centimeters of permanent displacement. Nothing in a 900-meter man span of a bridge, but reducing your seismic load by 30% is quite a good deal. Is the plan and elevation of the bridge? Again, I draw your attention to the height of the tower. This would be the highest tower in all of Manila, so they're very excited about that. It is a hollow concrete structure, basically reinforced, detailed for inelastic behavior, although it is going to be elastic. That's very important. This tower is actually governed, the loading, the actual thickness, reinforcement is actually all governed by wind loading. This is typhoon country. You have a very tall tower standing there, so the loading, and it has to be elastic, unlike seismic where you can accept some inelasticity. This one has to remain elastic. So this tower stiffness and strength was governed by wind loading. However, the detailing had to also be seismic. So that's your suspender belt system if you think about it. Obviously, by isolating the bridge at the bottom, we made the seismic loads lower than the wind. If we did not, the seismic would have been larger. Make sense? So it was governed by seismic until we isolated it. Once we isolated it, wind governed the loading. That was the same story across the whole bridge, by the way. In other words, by isolating the structure, we made the seismic loading, which would have governed the whole loading of the bridge, tower or marine structure, lower than the actual wind loading, which is typhoon loading coming in. The typical deck section is an orthotropic deck cross-section. This is one area, by the way, that is different than the San Francisco-Oakland Bay Bridge, because Caltrans there insisted on compact sections for the orthotropic deck. We did not believe it's necessary here. We decided we don't need to, because obviously it's a very, very long span, and having extra weight on the deck is just, extra weight that is not needed. That's the word extra. These are the elements that we have. Mainly we have them for adding damping. That's primarily why they're there. Now, you might think, what if these dampers don't work? Because we all know seismic dampers would leak. You are in Manila. Maintenance may not actually happen. What would happen? So we actually ran it with scenarios of one not being there at all, and another scenario, them locking up, and finding out what that does. And in both cases, the bridge is okay. You just sustain local damage to the various elements, but you don't have a problem with the overall performance of the bridge. The piers are also hollow sections as well. And the articulation at the pier is basically they have anchor ties at each bend. They have a bearing, and they have a shear key as well on those elements. And the other side of the expansion joint where the high-level approach comes in, the high-level approach is isolated between the superstructure and the top of the bearing. So the bottom image shows you the actual shock absorbers that you have there, which are actually there to resist wind loading. And once that threshold is exceeded, those break so that your isolation does actually take place. So in this case, what you have is a triple friction pendulum system that is over all of the marine viaduct as well as the high-level approach. And I call them, this is the image of the windlock. So you have the isolation system, which is there, plus a supplemental windlock that is there to resist the wind loads. And once that is exceeded by the seismic loads, those windlocks break, and you've got the unisolated structure. And that's therefore the maximum load that you're designing your foundation for is the wind loading, not more than that. And that's the bridge once it's built. As we speak, this South Channel Bridge is out for bid. We expect the contractors to come and put their bids in May, June. Award would happen later this year, and groundbreaking, if all goes well, later this year or early next year. We think 2030 is aggressive, but we're still pushing for that. Sounds like a good round number, and I think at a time of elections, it's a time that they would like to see it there. And with that, I end my presentation, and I'm available for questions if you have them. Otherwise, you can catch me in the hallways. Thank you. Yes.
You mentioned with the San Francisco Bridge about a probability analysis or a probability to determine your picture. What's the consideration of the sort of maximum probable of what can happen on either of those adjacent faults or nearby faults?
So we did look at that. Because the questions were asked multiple times, and we did run it and basically showed that the bridge performance is still acceptable and it's not an issue, but it wasn't in the criteria. So what's important is that the criteria did not include it, but when the questions were asked, again, the San Francisco-Oakland Bridge is probably the one bridge that's most peer-reviewed that you'd ever see. You can name probably about 4 or 5 peer reviews that happened during the lifetime of it. And that question was asked multiple times. So at the end of it, basically said, okay, let's get the maximum credible earthquake. Let's run it. Let's see what happens. And basically the bridge behaved the same way. The difference was that the displacements were a little bit larger. The demands were a little bit larger, but there was nothing that is any different in terms of its overall performance and ability to open after a major one. Thank you.
Work? Yep. We have some questions from the live Q&A on the app. First one, how were the active links in the towers designed and detailed for ease of replacement if necessary after a severe earthquake?
It's a good question. I did not specify that or show it's on the image, but if you go back and look at the PowerPoint, you'll see that they were bolted connections. So the intent was after an event, you would go in, and the first thing you would do is in the shear areas where there was a lot of yielding, you would actually drill holes, big holes, openings, so that the actual yielding or energy that is locked into those links will go away. And then after that, you'd come back and remove the bolts one by one, and then there is 2 shear links per panel, so you remove one, you put one, you remove the other, you put the other one.
Second question is, how were the active links in the towers, in the Manila Bridge, did you check for lateral movement of the tower base on the isolation layer under ULS wind loading? And if so, how do you accommodate this?
Yeah, so during wind loading, there was no movement at all. If you remember, I kind of implied it, but I'll say it again. Without the isolation, the seismic loads were higher than the wind load. And with the isolation, the seismic loads were lower on the bridge. So ultimately what happened is we made sure, so the isolation does not move during wind at all. It's the earthquake that exceeds that triggers that isolation to occur. And once that happens, the seismic loads are lower.
Next question is, should time history analysis become a regular tool we use in seismic design? It would definitely help with soil structure interaction, but it's often considered too complex for regular design in New Zealand.
Yeah, I would agree with that completely. I don't think time history is a tool that you want to apply on all your bridges. Like I said, a lot of times it's a good tool for long span bridges with very complex or difficult foundations. If the bridge itself is sitting on liquefiable soils and it's complex, it's curved, there's value to doing that. But in the most cases, I would say for standard bridges, it's probably just good enough to run with response spectrum.
Awesome. Next question is, how do you consider the compression buckling of the tower after the links are damaged?
Yeah, so there was no shaft compression buckling at all. The best way to think about it is the seismic loading, and even during the maximum credible earthquake that was mentioned, was such that all the fusing is happening in the shear links, and the actual shafts under no circumstance reach F yield. They don't even get close to F yield. So the elements are designed for 0.7, 0.8 by memory of F yield, which is very compact section, no problem with any of that. These are very well-stiffened elements. But we actually did test these elements for vertical compression. And I don't have the force displacement relationship, but I think a lot of people can imagine it. It's such that it reaches F yield, and as any compact section would do, it'll plateau for about 2 times F yield before it buckles. So the buckling of the compact section is the inelastic buckling that actually occurs. But it's, again, one of those safety nets that we have, not that the demands are going there in the first place.
And then last question is regarding the health monitoring on the Bay Bridge.
Yeah, so the health monitoring is very interesting. The bridge itself is very well monitored for seismic monitoring, accelerometers, all that. It doesn't have the health monitoring that we all are working with right now in the industry. Right now, there's all sorts of health monitoring systems that are applied. In fact, just finished another project in Canada, the Champlain Bridge in Montreal. There they have the bells and whistles on it. They wanted everything. I mean, we're having a database. You go into a computer room and you literally see the bridge breathing, and you have the mirroring. You have the displacement, what's actually happening today. They have the thresholds of the expansion joints, and this is green, this is red, and on a monitor you can literally know if the bridge is okay or not, or is there an area you're gonna go inspect it. So it's being monitored for temperature loading, wind loading, you name it. Same thing is happening in Florida. We're working on a project in Florida on Sunshine Skyway. It's an older bridge built by John Muir, but Florida is very interested in also health monitoring. So on the Bay Bridge, Caltrans did not want to have a maintenance and operation budget because they were always concerned that it could be cut. So what they wanted to do is not have that, however, have the ability to install that system if they need to.
Great. Are there any other questions from the audience?
Thanks for the talk. That was really great. What was the total cost of the Bay Bridge?
About $6 billion in total. It's, just to give you a perspective, the main span, the self-anchored suspension bridge, was about 1.7 billion, and the Skyway was about 1.5 billion, and the rest was the Oakland touchdown and the YBI, and then there's obviously other costs associated with running the job for 13 years that drew that up. The best example I've given folks, a bridge of a cable-supported bridge usually costs you, the cost of maybe a good Honda, that's per square foot. The self-anchored suspension bridge was about a Mercedes. So it kind of gives you a sense of what you're paying for in terms of that, aesthetics and whatnot that cost that. Comparatively, just to give you an appreciation of it, the Batang Cavite project in Philippines, it's about a Honda. It's actually more like a cheaper version of it as well, because I think the price will be very competitive in that market. You had a question?
No, well, it's related to the health monitoring. You said that there wasn't huge sophistication with San Francisco Bay Bridge. What can you say about any long-term displacements that have occurred during the time it's been there?
You're talking about what happened since it opened to traffic? Not much at this point. I'm not sure there's nothing really that happened. However, what's important is Caltrans have a very sophisticated maintenance and operation that they do on all their bridges. Remember, these guys have been maintaining the west spans of the Bay Bridge since 1930s, Golden Gate on the other side, Carquines. So they have a very good maintenance program that they do out there. They go walk the cables, inspect everything. So it's being maintained quite a bit. It's just that they're not ready to use the technology. It's a matter of time, but they're not ready to use the technology yet.
We have some more questions from the app. Do both bridge superstructures, including the suspension cables, were they designed as elastic structures?
Yes, that is the primary focus on making sure that your structure is functional. If you think about it in many ways, you need to have your deck to drive on it, and you need to have your support system, which is the stays or the suspension cables there. I will mention that expansion joints are designed for these very large relative displacements on both structures. But if you look at any images after an earthquake, you find these expansion joints basically popping out and flying in the air, not there. So we have actually told the clients that the first thing you do is you go with big steel plates, you put them over the expansion joints so that you can have emergency traffic. And we told them that the speed limit at that point is not 50 miles an hour. Maybe you drive over the expansion joint as smaller piece, low speed.
And then last question on there is, did your bridge over in the Manila Bay, did you put any piles on the island?
No, we did not. In fact, we have not touched the island yet because it is protected. They intend to have a major tourist project all about it. I suspect that before 2030, that project would start. We have the plans of exiting into the island. It's a big coral reef. If anybody goes there, it's a beautiful area to dive. And I suspect once they have it there, there's going to be buildings and hotels and you name it.
And then does the isolated tower have the ability of self-centering? I'm assuming it's referring to the Manila Bridge.
No, it doesn't. It doesn't. It really is designed so that if the maximum displacement is 30 centimeters, we checked what would happen if it remains at 30 centimeters and not go back to 10 centimeters, and found out that it's okay. Again, put it in perspective. I give you a simple example. Akashi Bridge, when it was being built in Japan, the earthquake occurred there. And I think that, if I remember, one of the towers moved about a meter relative to the other one, but they did the status and found out that it's okay. So it's in simple terms, again, imagine we build everything in construction to a tolerance. Nothing is perfect. We cannot build everything perfect. So if you do everything 1 to 1,000, that's pretty darn good. That's a good accuracy. So if the tower is 300 meters tall, the tolerance accuracy is about 30 centimeters, right? So it gives you that displacement is very small, and it says when the accuracy of construction.